In Chapter 16 of the Seaborg text, we're going to cover sections 16.1, 16.2, and 16.4, which introduce three advanced strategies for feedback control loops: cascade control, time delay compensation, and selective control. In cascade control, there are two nested feedback control loops that are used in tandem to improve the dynamics of the process. The output signal from the primary controller, or the master controller, provides a set point for what's called the secondary controller, or the slave controller. The slave, or secondary control loop, is nested within the master, or primary control loop. In cascade control, there are two sensors, two controlled variables, and just one manipulated variable. Although there are two controlled variables, the operator only provides the set point for the controlled variable in the master control loop. The master control loop then selects the set point for the secondary or slave control loop. The secondary control loop should have faster dynamics than the primary control loop. To understand how cascade control works, we'll introduce it by way of an example. Consider the temperature control loop on this jacketed stirred tank reactor. Presumably, the reaction occurring here is exothermic, and heat must be removed from the reaction to maintain constant temperature. That heat is removed by a jacket containing circulating cooling water. A control valve on the cooling water makeup is used to manipulate the flow rate of the incoming cooling water. This control valve on the cooling water out line is used in a level control loop for the water surge tank. One way to control the reactor temperature would be to measure the temperature of the fluid in the reactor and use that signal in a feedback control loop to decide what the flow rate should be in the cooling water makeup. This process may have significant time delays and time constants because heat must be transferred from the cooling water to the jacket, and then from the jacket across this thermal boundary representing the reactor wall to the contents of the reactor. The residence time for the water in the circulation loop represented by the cooling jacket and the residence time for the process fluid flowing through the reactor are time constants that will both appear in the feedback control loop. Additionally, there are time constants associated with the heat transfer. Suppose that there's a positive perturbation in the cooling water temperature. At some later time, the temperature of the reactor contents will also go up. The controller should then allow more cooling water into the jacket. But the temperature of the fluid in the reactor that's being measured, T, will not respond immediately when Tc goes up due to heat capacities and thermal conductivities. As additional cooling water is added to the circulation loop in the cooling jacket may cool too much, quenching the reaction, or leading to an oscillation in the reactor temperature T. Therefore, in order to ensure the stability of the feedback control loop, the controller gain must be set to a small value. The dynamics of this process could be improved substantially by using cascade control. Cascade control introduces a second feedback control loop. In this scheme, the reactor temperature is measured and sent to a temperature controller, which then chooses a set point for a feedback control loop on the jacket temperature. Now, if the temperature of the cooling water circulating in the jacket goes up, the valve will open as soon as the perturbation in the jacket temperature is measured. This will enhance the control of the reactor temperature. Note that this is not a feed-forward control loop because both the reactor temperature and the jacket temperature are being measured, and those are the two controlled variables. Cascade control can be represented by a generalized block diagram like the one shown here. The operator supplies a set point for the master or primary control loop. Y1 is the controlled variable for the master loop. The error signal in Y1 is then used in the primary controller. The output of the primary controller is a set point for the secondary or slave control loop. In our jacketed reactor example, Y1 would represent the temperature of the contents of the reactor, and Y2 would represent the temperature of the cooling water circulating in the jacket. In cascade control, there's only one manipulated variable. So there's only one valve, and that valve is inside the secondary control loop. Here we show there can be disturbances that affect Y2 and disturbances that only affect Y1 without affecting Y2. GP2 here describes how the manipulated variable, which in this case is the flow rate of the cooling water makeup, affects Y2, which is the temperature of the cooling water circulating in the jacket. GP1 then is the process transfer function describing how the temperature of the water circulating in the cooling jacket affects Y1, the temperature of the reactor contents. Let's look at the regulator transfer function that describes how disturbances D2 affect the controlled variable Y1. That transfer function contains both the inner control loop and the outer control loop in the denominator. If both control loops are approximately first order, then the characteristic equation is second order in S. If the secondary loop has faster dynamics than the primary loop, that is, if tau2 is less than tau1, then the dynamics will be faster than if the characteristic equation were based only on the outer or the master control loop. To show how cascade control can improve the responses of feedback control loops, let's consider a case that has a higher ordered transfer function for GP1 and a very fast transfer function for GP2, which is just a gain. In this example, the primary control loop has been tuned with a PI controller, and the secondary control loop has been tuned with proportional only control. When there's a step disturbance in D2, we can say that using PI control only in the primary loop with no cascade control, that is, no secondary loop, there's a significant disturbance in the controlled variable. However, when the secondary loop with a P-only controller is put online, the response to disturbances D2 is greatly improved. The response to disturbances D1, which remember, do not directly affect the controlled variable in the secondary loop, is also improved a little bit when using well-tuned cascade control loops. Often, cascade control is used with a PI controller for the primary loop and a P-only controller in the secondary loop, as was done in this example. If the secondary loop cannot tolerate much offset, PI control can also be used in the inner loop. Derivative action is only very rarely used on the secondary control loop, but a PID controller may be used to speed up the dynamics of the primary control loop.